Oh boy, this looks important. It sure is, friends. This is the fundamental theorem of calculus that if it's continuous on a closed interval, a function, then we are able to find its antiderivative. And all you got to do is you find the antiderivative and then you subtract the top value from the bottom value of the function. So you antiderive to figure out what the original function is. You plug the top value into the function and you subtract that away from the bottom value of the function. And we show that often by like kind of putting like a little vertical line thingy and then putting B and A on there. And then you just start evaluating the thing. Now, one thing to note is we are not doing indefinite integrals. So where there isn't a value here, if there wasn't a value there, once we integrate, it would just be f of x, and then there would be the plus c thing. Okay. There is also this thing that we're going to talk about today, but that's going to be in the later part with the second fundamental theorem of calculus, which is kind of like this sort of like inverse operation, derivative, antiderivative thing. And so those two actions undo each other, and you're left with just f of x. But more about that later. Let's play around with this fundamental theorem of calculus. So we want to evaluate this definite integral. We're not going to do rectangles or nothing. We are just going to figure out what it is. So to do that, we do our power rule backwards integral thing, but it's got like this squared and it's not quite on the t. It's like of that parentheses thing. We don't want to deal with that. I'm just going to whoop, whoop. We're just going to actually square that thing to make it a 4t squared. Ooh, that's an ugly t. Minus 4t plus 1 dt. I think I followed that properly. Checking my notes, making sure I did that right. It just doesn't, it feels bad in my bones. Oh, no, it's right. My bones are good. Okay, so now we can do that antiderivative trick where we add 1 to the exponent and we divide by our new exponent. So that's going to be 4t to the third divided by our new exponent, which is 3, minus 4t to the second divided by our new exponent, which is 2. Then we just have a constant. So guess what? Constant, you get a variable, t. Then we, just as a note to say that, hey, this came from a definite integral, we're supposed to do this between 0 and 1. So we plug them things in. We don't do the plus c, no plus c, but we plug these things in. So first we do the 1. We do the top minus the bottom. So that's 4/3 times 1 cubed. 4 divided by 2, excuse me, is just 2. And then 1 squared plus 1 times 1. And then we got to subtract what happens when we put in 0. Well, if we put 0 in that 4/3 with a t, that's 0. Minus 4/2 times 0, 0. Plus 1 times 0, well, that's also 0. So we're not going to be subtracting anything. It's just that pink stuff that we've got to evaluate. So that's 4/3 minus 2 plus 1. So that is a number. I think it's 1/3. 1/3. Yeah. And we can confirm that on our graphing calculator. Let me show you how. So on my calculator, I've typed in, and I went with the 2t minus 1. We could have done this one too, but I just wanted to make sure I didn't FOIL that wrong. I also adjusted my window. If you want your window to match my window, this is how my window works. And then here's my graph. Great. To calculate the integral on the calculator, if you press second and then calc, here is an integral thing. Oh, cool. So we hit 7. My lower limit is 0. And my upper limit is 1. And then boom, it calculates it for us. So this shaded area, that's the area that we're trying to find. Note that it even came in 2 pieces, but don't freak out. It's fine. So we get 0.3 repeating. Oh, that's the same as 1/3. Great. All right. Doing it again. Now, this one has got all kinds of weird bits to it, so I don't really want to try to integrate that thing right away. I want to clean it up a little bit, so it's an integral that I can find a little bit more easily. So that's 1 over the square root of u minus the square root of u over the square root of u du. Okay, so that is u to the negative 1/2. And the square root of u divided by the square root of u is just 1. Neat. Okay, now I'm ready to integrate. So I add 1 to that 1/2, so I get u to the 1/2. And then I divide it by its new exponent, which is 1/2. Then that negative 1 gets a u stuck on it, so that's u. So we're going from 1 to 4. So that u to the 1/2 divided by 1/2, that is just 2 square roots of u. And the u I've got first is the 4 minus ru, which is 4. And then we got to do this all for the 1. So minus, again, 2 square root of u, which is 1, minus 1. Okay, so square root of 4 is 2. 2 times 2 is 4. Minus 4, minus 2, minus 1. So that is negative 3 for our thing. And we can check that on the calculator because this one was a bit weird. Okay, so I've typed this into my calculator. And then if you want to have the same window as me, this is what I set my window to be. Here's my graph. So I need to check this from 1 to 4. So we're going to calculate the integral 7 from 1 to 4. Boop. And we get a negative 1, not a negative 3. Why did that happen? It's a good thing we checked. Oh, I found it. I missed parentheses here. So that's 2 minus 1. So that is 0 minus 2 minus 1 is 1. And so there we go. We got negative 1. Good thing I checked it. It was a silly thing that I missed. Sorry about that. But yeah, we get negative 1. No problem. All right. Now, this one has a bit of a sneaky trick to it. When you look at the graph, it actually dips down below the x-axis. So we've got an upper part and we've got a lower part. Since we have that upper part and lower part, we could just integrate and we would get a value. That's fine. However, this one's looking for keyword being total area between the curve and the x-axis. So this chunk right here is going to get a negative value since it's below the x-axis. But this problem, since they want the total area between the curve and the x-axis, we need to make that red part positive. So there's weird, complicated ways to do it. But what I think would be easiest is if we find that blue area and then find the red area and just make sure that the red area turns positive and then call it a day. Now, we could do that geometrically because they're just triangles, but I think it's worth seeing these steps worked out using our fancy methods, just so that we can see an example with fancy methods. So instead of doing the integral from 0 to 3, we're going to do the integral from 0 to 2 of 2 minus x. And then we're going to add the integral, well, the absolute value of the integral from 2 to 3 of 2 minus x. Oh, this needs a dx. This needs a dx. It really should be blue, too, because that's the blue area. Now, you could do other goofy stuff, like you could, instead of like doing the absolute value, you could just whatever. You could do the opposite direction. So you could do the integral from 3 to 2, because that would turn the red part negative, because that would add a negative onto it. You could just not even add them yet. It's whatever. You do you. Okay. I'm going to do the blue part first. So the antiderivative of 2 minus x, that is going to be 2x minus x squared over 2. We're going to check that integral from 0 to 2. Then the other one is going to be the same thing from 2x minus x squared over 2. And then this one's going to be from 2 to 3. So taking care of the purple part, we would do the top. So that's 2 times 2, which is 4, minus 4 divided by 2. And then we would subtract, well, if I put 0 in both of those spots, I just get 0. Okay, so nothing really is going to happen there. So that's the purple bit. I don't know why it's highlighted in red. It's fine. Then we do the other part. So that is going to be 2 times 3, which is 6, minus 9 halves, minus, now this, the red, the 2 is going to get us stuff. So that is 2 times 2, which is 4, minus 4 square, 2 squared divided by 2, just 2. So that is 6 minus 9 halves, so that's 12 halves minus 9, so that's 3 halves minus 2, so that's negative 1 half. But remember, way back at the beginning, we did the absolute value of all that stuff. So it's the absolute value of all this stuff. So it's the absolute value of that stuff right there. So that's going to become a positive 1 half. So you could do that absolute value as you're going along, or like I did, just take care of it at the end. Now this teal section over here, 4 minus 2 is 2. Minus 0 is just that. So then our overall area between the curve and the x-axis is 3 halves. Now again, if you had just found the antiderivative from 2 to 3, you would have gotten, I didn't even add those right. You would have gotten 3 halves, but I didn't add these right. This should be 5 halves. So if you had done it incorrectly and done from 0 to 3, you would have gotten 3 halves. You would have done 2 minus a half. But this asked for the total area of the region between the curve and the x-axis, so we needed to make this region positive. If they just asked for find the antiderivative from 0 to 3, then yeah, integrate, be done.